All right, y'all. So this is the Clausius Clapeyron equation. Notice how the t's are outside. They're not underneath with the r. And the r value that you're going to use, r is a constant in this. So r is equal to 8.314. And the unit on that is joules over moles times Kelvin. The Kelvin is on the bottom. And let's see. Then the next piece of information is that your P units over here, the P's can be different numbers. They're going to be given to you. But they just need to be consistent with each other. Delta H usually comes in the form of a kilojoule per mole. And that's great for the mole part because you can see the moles are going to cancel. But you'll notice, of course, that the kilojoules and the joules, they don't cancel properly. So we have to watch for that. Now, the T value, remember, use your R to help tell you what something's going to be. The T values have to come in Kelvin. So we are going to put that number in as a Kelvin and that number in as a Kelvin. Some people get all tied up with this. They want to use the natural log relationship that they remember, that natural log when you have like P2 over P1, that's the same thing as the natural log of P2 minus the natural log of P1, or just as a reminder, P2 times P1 is the natural log of P2 plus the natural log of P1. You will not need those relationships for this equation. It's just that sometimes people get all caught up in trying to remember that relationship, so that's why I'm mentioning it, but you won't need it in this one. What you will need and what you will see us using is when you solve, if you have to solve for P2 or P1, either one of them, that's going to be an unknown inside a natural log. And you'll see me working problems with this, but you have to do e raised to the, and you have to do it on both sides. This is a relationship like in logs. You might see it with logs, like if log of n is 5. Then you do 10 raised to the log and 10 raised to the 5. Those cancel, and you get n is equal to 10 raised to the 5th. And you can actually put that in your calculator, and now your variable isn't inside a log. However, in this case, it's a natural log. It's the same idea, but natural logs are base e, which is like 2.3 something. So we have to use e raised to the. So again, if we'd had the natural log of x is equal to 5, it would be e raised to the, that cancels that part out, and you get x is equal to e raised to the 5th. So that's that relationship. That's what we're going to use when we solve this one. All right, so most of the time you're going to be solving for delta H or P2. You may have to solve for you could solve for P1, but most of the time it's P2 you're solving for, or temperature 2 that you're solving for. The examples I've got here are going to be, I've got a P2 example and an H example. There's a T example if you want to see it in the textbook. All right, so, whoops. My first problem is going to be over here, and it's, if you'll notice in the given problem information, we have a P1, so that's good. We have a P2, we have a T1 and a T2, and it wants us to solve for delta H. So I'm going to go back over to this one here. So to solve for delta H, we have to get the H all by itself. So we want to multiply both sides by R and divide both sides by this term right here. So I'm going to move that, and then... So it's like I'm just saying, divide both sides by that number. And then divide both sides by that number. So when I do that, these terms go away. So I'm going to go ahead and erase them now. But I've still got the R with the H, and you have to solve a variable, it has to be by itself. So times R and times R, these R's cancel. So I'm left with delta H is equal to this equation. Now, I will say that if you go to Google this online, I actually learned a different version of the equation, and it was with a negative H, and then these two were in opposite positions. So don't let it startle you if you are going other places to watch some more people use this equation. You might find the negative version of it. You still get the right answer, like I said, because those t terms are flipped. All right, so that's the equation we're going to be using for this one over here. And you'll see that's what I have set up right here. So this is just plugging things in. So what I'm going to do is show the next step right here, plugging numbers in. I'm just going to try to make it look a little bit better here. So if this is P1, you'll see that I put P1 over here. And then if this is P2, P2 is right there, because that's where it goes. It's in the higher position. And the R is a constant, the 8.314. Let's see, and then my temperatures with this version of the equation, if T1 is 200, notice it falls there, so there's my 200. And then my T2 is at 300, and it falls over here. Then I'm going to put that in the calculator. Clear it off. So I've got to keep in mind the final answer is going to come out to being joules per mole, because this Kelvin right here is going to cancel with these kelvins here. Because, you know, when you subtract, you're going to get like 1 over Kelvin. It's going to be your unit. And basically, I've got a 1 over Kelvin on the top right there. So my final unit is joules per mole, which makes sense, except that it's going to end up wanting to be in kilojoules per mole. All right, so 8.314 times the natural log of, and we've got 100 divided by 10. And if you want to just say the natural log of 10, that's totally fine. Divided by, parentheses, 1 divided by 200, parentheses closed, minus 1 divided by 300, parentheses closed, parentheses closed. And that's a nice even little equation right there. So there's our number. And remember, that's joules per mole. To get it into kilojoules per mole, which is a much larger unit, I'm going to divide by 1,000. So 11.46. So you can see right here, that's the full one. And then this is the actual answer. You'll be told how far to round this in regular problems. All right, so let's see it solved for a different position. I'm going to go back over here to this version. And remember, let me bring it down just a little bit. I've got the ln of P2 over P1 equals delta H over R 1 over T1 minus 1 over T2. Let me make sure that actually, yeah, that one has the T1 in it. This is T1. This is T2. The natural log of, and then P2 is going to be what I'm solving for. So I need e raised to both sides. And when I do that, that'll come out, and I'll have P2 over P1 is equal to this whole term right here, e raised to the delta H over R times 1 over T1 minus 1 over T2. I'm used to the other version. It's T2 minus T1. And then I'm just going to multiply both sides by P1. And I don't want that in the exponent up there. I want it the whole thing times P1. And that's going to get my P1 term to cancel. I'll just have P2. So if you look over here, that's what I've got for this equation. And notice it says find P2. That's how I know I need to solve for P2. So you can see I've got the equation all set up right here. So I'm going to just plug my numbers in again. So just to double check where everything is. So here's 10 kPAs, and that's for P1. Oops. And then double check my other numbers. The delta H is put in as a kilojoule per mole, and my as a joule per mole, because it was a kilojoule in the problem, but I need my joule terms to cancel. So I need that term to cancel with this one, which is joules per mole per Kelvin, and those units are both kelvins. So those are all going to cancel, which is great, because when you are in an exponent, you're unitless. And let me, oh yeah. So over here, 200, that's T1, so that's first. And then over here, T2 is right there. I'm going to put in my equation. Now, we can all do it in the E exponent range, but I'm actually going to just do it without it being in the E range because it's actually a little bit less work to do it this way. So watch how I'm doing this one. So 30,000 divided by 8.314 times parentheses 1 divided by 200 minus parentheses 1 divided by 300 parentheses close. So that's my exponent region. I'm going to push enter. Now I'm going to use my little E key, and this calculator lets me use the answer. So it plugs in the answer, the most recent answer you just solved for. So that's going to be plugging in that 6 number into the E, and it saves it to lots and lots of decimal places. So that's really nice. And then don't forget the 10 over here. So times 10. So 4090, and the unit on that is kilopascals, and I knew that because all the units in the exponent region canceled, but the kilopascals over here, they came from the P1 value. They didn't cancel out, so that's how we know it. P2 is. I was solving for P2 the whole time.